In this elementary algebra review tape, we're going to be going over our work on geometry. We'll be doing several examples. We'll be going rather quickly. If you have any trouble with any of the particular problems, then of course you should go back and look at the original videotape lessons on geometry. In our first example, we have here a triangle. We notice that two sides have the same length, so it's an isosceles triangle, and we're interested in finding angle A. Okay, since it's an isosceles triangles and we have two equal sides, the base angles are also equal. That is, angle A is equal to angle B. Let's since they have the same value, let's represent them both by x. Whereas angle A has x degrees and angle B has x degrees. Okay. Now, the sum of the angles, the interior angles of a triangle, is 180 degrees. So we can find angle A in the following fashion. We can say that x plus 50 degrees equals 180 degrees. The sum of the angles of the triangle. They add up to 180 degrees. X plus 50 is 180. 2x plus 50 degrees is equal to 180 degrees. Subtracting 50 from both sides, 2x equals 130 degrees. And finally, dividing both sides by 2, we get that x equals 65 degrees. This is 65 degrees. This is also 65 degrees for a total of 130, and 50 for 180 degrees. In example number 2, we are interested in finding angle x. Now let's look and see what we have. We have three parallel lines. The arrows indicate that these lines are parallel to each other. I've drawn a transversal line which cuts across these parallel lines, and it forms an angle of 110 degrees with this line over here. We extend it till we hit down here, and then if we were to draw a line up here, this would form an angle of 30 degrees with this line over here. And angle x is down here. We're interested in finding x, given this setup. All right, we need a way of going from 110 degrees down to this area. Now we have parallel lines cut by a transversal. The corresponding angles are equal. Let's denote these angles 1 and 2. Since we have these parallel lines cut by a transversal, the corresponding angles are equal. Therefore, angle 1 must be also 110 degrees. So now we're down at least to this general vicinity. If angle 1 is 110 degrees, notice that angle 1 plus angle 2 together, they form a straight angle, 180 degrees. So angle 2 must be 70 degrees, or 180 degrees minus 110 degrees. They're supplementary angles. Together they add to 180 degrees. Angle 1 is 110 degrees, therefore angle 2 is 70 degrees. All right, now we're inside this triangle. We already know that some of the angles of a triangle is 180 degrees, so all we have to do is say that angle 2 plus 30 degrees plus x must be equal to 180 degrees. Angle 2 is 70 degrees, so 70 degrees plus 30 degrees plus x must be equal to 180 degrees, or 100 degrees plus x must be equal to 180 degrees. And subtracting 100 degrees from both sides of the equation, x comes out equal to 80 degrees. X is 80, 30 is 110, and 70, 180 for this triangle over there. Okay, now let's consider in problem 3 the following right triangle. This leg we will represent by x, this by x plus 7, and the hypotenuse, the side opposite the right angle, has length 13. And I'm interested in finding the area and the perimeter of this triangle. And it's a right triangle. Okay, in other words, we need to figure out what x is. If we could figure out what x is, then we'd know what x and x plus 7 were. The area of a triangle would be 1/2 base times height, or in a right triangle, 1/2 the product of the legs, because we can think of one leg as the base and the other one as the height. And to find the perimeter, that would be simply the distance around the sum of the lengths of the three sides. Okay, so the big thing here is to find x. And we'll find x by using the Pythagorean Theorem. It is a right triangle, and therefore, in a right triangle, we have that the sum of the squares of the two legs is equal to the square of the hypotenuse. Okay, so x squared plus x plus 7 squared must be equal to 13 squared. A squared plus b squared equals c squared. The sum of the squares of the two legs is equal to the square of the hypotenuse. Okay, let's work with that. X squared. Now, x plus 7 squared is x plus 7 times x plus 7. And using FOIL to expand that, we'd have x squared plus 7x plus 7x plus 14x plus 49 equals 13 squared, or 169. Let's collect like terms. We have 2x squared plus 14x plus 49 equals 169. We have a quadratic equation, and it's convenient to get everything over on one side equal to 0. So let's subtract 169 from all parts, from both parts of this equation. We have 2x squared plus 14x. 49 minus 169 gives us minus 120 equals 0. Okay, we'd like to solve this quadratic equation. We're going to try to do it by factoring. The first thing, of course, we look for is a common factor, and we can pull out a 2, leaving us with x squared plus 7x minus 60. 2x squared plus 14x minus 120 if you multiply it back out. Okay, we have 2 times x squared plus 7x minus 60 equals 0, and we are looking to factor this trinomial. We're looking for two numbers which multiply to minus 60 and add to plus 7, and they are plus 12 and minus 5. So we can check that. X squared minus 5x plus 12x, that's plus 7x minus 60. We have the product of two numbers, well, actually three numbers equal to 0. Obviously 2 can't be equal to 0, but either x plus 12 could be 0 or x minus 5 could be 0. This gives us x equals minus 12, and this x equals 5. Since x represents the length of a side of this triangle, we will reject the minus 12 answer. And we have x equals 5. And you, of course, could check this. We have x equals 5. Let's see what our triangle comes out looking like. X equals 5. X plus 7 is this leg here. 5 plus 7, this is 12, and this is 13. A 5, 12, 13 right triangle. It is true that 5 squared plus 12 squared is equal to 13 squared. You can check that out. Now, back to area and perimeter of the triangle. The area is going to be 1/2 base times height. And as I mentioned, in a right triangle, one leg could be thought of as the base and the other one as the height. So 1/2, 12 times 5, and 2 goes into 12 6 times, and that leaves us with 30 square units for the area. If they had been in inches, then this would be 30 square inches. Now the perimeter. The perimeter, the distance around the triangle, the sum of the lengths of the three sides is 5 plus 12 plus 13. And that comes out to be 5 plus 12, 17, plus 13, also 30. But this is 30 units. If it was in inches, it would be 30 inches. In our fourth example, we are going to have the following setup. We have a right triangle, like so. And somewhere in here, we are going to draw a line segment forming another smaller right triangle, which is contained inside the larger one. Okay, suppose I tell you that this leg has length 9, this leg 6. This, from here to here, this is 8. And x represents from here to here. X does not represent the entire leg here of the larger right triangle, but rather just from here to here. And we're interested in finding x. And what we have here is a setup for similar triangles. These two right triangles are similar. You'll notice, of course, they each have the right angle. They share this angle down here. And since the two angles are the same, the third angles must also be the same, because the sum of the angles of the triangle would be 180 degrees. So each angle in one is equal to the corresponding angle in the other. So we have similar triangles. Now we can set up a proportion in order to find x. Okay, now we're going to be working with the two triangles. We have a small right triangle and a big right triangle. We're going to try to set up we know that corresponding sides of similar triangles are in proportion, and we're going to set up such a proportion. All right. Let us take the right triangles. The larger right triangle has a long leg and a short leg. The smaller right triangle has also a longer leg and a shorter leg. So let's set up the following proportion. X plus 8. The long leg of the big right triangle is to 8. The long leg of the small right triangle as 9. The short leg of the big right triangle is to 6, the short leg of the small right triangle. Okay, what we have here, long leg is to long leg as short leg is to short leg. And in both cases, we are working with the larger right triangle on the top and the smaller one on the bottom. That's not important. You could have done that in reverse order. Okay, you see the proportion. X plus 8, the long leg, is to 8, which is the short leg, which is the long leg of the smaller right triangle, as 9, the shorter leg, is to 6, the shorter leg in the smaller triangle. Okay. Now, it is important that you don't make the mistake of saying x is to 8 is 9 is to 6. Okay? 9 and 6 represent legs of the right triangle. 8 is also the length of a leg. X is not. The leg goes from here to here. It is x plus 8. So it would be incorrect to write 9 is to 6 as x is to 8. You do need the x plus 8. All right, now that we've set this up, we have a fairly simple equation. It involves fractions, so we're going to get rid of the fractions by multiplying both sides of the equation by the LCD. In this case, the numbers 6 and 8, the lowest common denominator is 24. Okay, You could also, because we have just one fraction equals to another fraction, solve this by cross-multiplying, but that wouldn't even help you that much in this case. In fact, in other words, you would eventually have to reduce. The 24 works better than, for example, using a 48, which is in a sense what you're doing when you cross-multiply. So let's say the LCD is 24. We multiply both sides of the equation by 24. 8 goes into 24 3 times, leaving us with 3 times x plus 8. 6 into 24 goes 4 times 9. 3x plus 24 equals 36. Subtracting 24 from both sides. 3x equals 12. Dividing through by 3, x equals 4. So this is 4. The entire leg here is 12. 12 is to 9, as 8 is to 6. Or 12 is to 8, as 9 is to 6 would work out when you check it. Some people, by the way, prefer to designate the long leg of the larger right triangle, say y. And then they can say y is to 8. Y is to 8 as 9 is to 6. They solve for y. And at the end they say, well, y is x plus 8, and they figure out what x is. That is an option open to you if you so desire, or you can work in terms of the original variable x. Okay, our next example is a problem involving a circle. And what I want to do is to find the area and perimeter of not of the whole circle, but of the sector that is indicated in this diagram. And if you think of this like a pie, a sector is like a piece of the pie, and I'm interested in this sector. Okay, I'm cutting the circle, 2 radii, and let's say this angle is 30 degrees, and the radius is 6 inches. I'm interested in the area and the perimeter of the sector. This sector. Okay, now we know, assume that we know the area and the perimeter of a circle. The area of a circle, of course, is pi r squared. That's the area of the entire circle. And the perimeter of a circle, also known as the circumference, is 2 pi r. Okay, and what we're going to do is say, well, this is a portion of the circle. Figure out which portion of the circle it is, and take that fraction, okay, of the entire area of the circle. And the way we figure it out is that this sector is generated by an angle, a central angle here of 30 degrees. Now, what about the entire circle? Okay, if we go all the way around, that would be 360 degrees. So the entire circle, you could say, would be generated by an angle of 360 degrees. So we're talking about an angle 30 degrees. So this sector is 30 over 360, or 1/6 of the entire circle. Uh, 30 over 360, that's 1/12 of the entire circle. Okay, the entire circle will be generated by an angle of 360 degrees. This is generated by 30 degrees. 30 over 360, 1/12 of the entire circle. So to figure out the area of the sector, we would say it is 1/12 of the entire area of the circle, 1/12 of pi r squared, 1/12 pi times 6 squared, 1/12 times 36 pi, which is 3 pi. Now let's see. R was in inches, so this is inches times inches. This is in square inches. So the area is 3 pi square inches. And in a similar fashion, we can figure out the perimeter of the sector. Now, the perimeter of the sector represents the distance around the sector. We will have, it has 2 radii as boundaries, so we need 6 plus 6 plus the length of this arc. Let's say S represents the length of the arc. So the perimeter would be 6 plus 6 plus S. Now, how do we figure out S? S is a certain portion of the distance around the entire circle. It's a certain fraction of the total circumference. What fraction? 1/12. If the sector is 1/12 of the entire circle, then this is 1/12 of the entire circumference. So we have S is 1/12 of the entire circumference, which is 2 pi r. 2 times pi times r, which is